our chairman of NCM, Professor J.K. Verma from IIT Bombay, who is the one of the speaker for today's session. And we are blessed to have such a great personality among us in the field of mathematics today. Please unmute all because I am not visible. So I'm just saying, I just requesting you all, please unmute all and give a round of applause to him in respect of it. Thank you. Thank you so much, sir, for joining us today and accepting our invitation for delivering the lectures during this workshop.
Yeah, thank you, Sunita. I'm trying to adjust my iPad.
Yes, sir. Now I'm just requesting to Dr. Sudeshna. Dr. Sudeshna, are you there?
Yes, I'm there.
Yeah, Dr. Sudeshna is head of the Department of Mathematics. So I'm just requesting to ma'am, please introduce to sir.
Yeah. Very good evening to all of you. As I have already introduced myself in one of the previous sessions, I am head of the Department of Mathematics of Amity School of Applied Sciences. So again, it's a great honor for me to introduce today's speaker to the gathering. So Professor J.K. Verma is from the Department of Mathematics, IIT Bombay. Sir, I also welcome you from my side. Thank you so much. Professor Verma has done his PhD from Purdue University, USA in 1987. His primary research area is algebra. Professor has guided more than 15 PhD scholars and many master students. He has published over 70 research papers of high quality in peer-reviewed reputed journals and conferences. Professor Verma has organized more than 30 workshops and conferences on algebra. He is the fellow of International Center for Theoretical Physics, National Academy of Sciences, Allahabad, Indian National Science Academy, New Delhi. His achievements have been recognized by many different awards, which includes S.P. Bhattacharya Award for Excellence in Research in 2021 and Excellence in Teaching Award in 2016 from IIT Bombay. It is such an honor for us to have you over here, sir. Thank you so much again for joining and giving your presence with grace. Thank you so much for your time, and over to you, sir. Thank you.
Thank you, Dr. Sudeshna Ghosh. I really appreciate your efforts to organize this online program.
Thank you, sir.
Yeah, so we will start these lectures on matrix groups, but I need to share my screen. Just a minute.
Mm-hmm.
Yeah, share content.
Yeah, there's a green button like the share screen after chat.
Yeah.
Yeah. Yeah.
Okay. Can you see?
Yes, sir.
All right. Okay. So let us start. I have planned 5 lectures and 1 tutorial on some geometric aspect of matrix groups. So you have been exposed with the basics of group theory, finite group theory. I want to speak about matrix groups, which can be finite or infinite. The matrix groups are fundamental. They have been studied from many points of view. I will bring in a little bit of geometry so that the matrix groups acquire some life and prove a bunch of very beautiful results on matrix groups. And what I speak about is just the beginning of a beautiful area in mathematics called Lie groups, which is a systematic study of groups of matrices over fields of real numbers, complex numbers, over the ring of quaternions, or one can take finite fields. And the results about matrix groups are central to many areas in mathematics, such as topology, number theory, algebra, and algebraic geometry. So we will touch on some very basic things about matrix groups. So let me begin. So I will use F for any field. And most often, F will be the field of real numbers or F will be the field of complex numbers. And we will look at n by n matrices over this field. So this is the set of n by n matrices where the entries are in this field F. Okay. So because the entries are in this field F, we can add matrices. If A and B are n by n matrices, we have the operation of addition. Okay. So under addition, MNF is an additive abelian group. And if the field is finite, it's a finite group. If the field is infinite, it is an infinite group. And if n is bigger than 1, so under addition is always commutative operation. But if you look at multiplication, okay, as the binary operation, if A and B are multiplied, then the set of invertible matrices, which is denoted by GL and F, okay, that is a group, because the invertible matrix has an inverse, but very often it is a non-abelian group. If n is bigger than or equal to 2, then GLNF is a non-abelian group. Okay, for example, you just look at these two matrices, 1 0 0 0 and 0 1 0 0. So if you multiply these, we will get 0 1 0 0. But if you multiply in another way, then it is the zero matrix. So these two products are not equal. So over every field, a field contains 0 and 1. Okay, any field contains 0 and 1, and 0 is not equal to 1 in a field. So GLNF for n bigger than or equal to 2 is a non-abelian group for every field. Okay, so these are, because of non-abelian nature, they become quite interesting. In some sense, GLNF contains all groups, because suppose, all finite groups. Suppose G is a finite group. If G is a finite group of order n or order m, then by Cayley's theorem, I think this was proved last week. So by Cayley's theorem, okay, G is a subgroup of SM. SM is the symmetric group. On M letters. And if you remember how it was done by multiplying every element by a fixed element, and that permutes the element of G, and then you associate G with that permutation. Yeah. So if I take G from G, and then I use G, okay, by left multiplication. So LGH equal to G times H for all H. Then LG from G to G is a permutation. Yeah, by cancellation, LG is from G to G is a permutation. And so we just define this map phi from G to SM. Phi maps this element G to left multiplication by G, and this is an element of SM, and this is injective. Okay, you have seen in Professor Om Prakash lectures that phi is injective. So every finite group injects into the symmetric group on M letters, where M is the order of the group, but the symmetric group itself is isomorphic to the group of permutation matrices. So this LG is a permutation, and you take the identity matrix, and permute the rows according to this permutation. So suppose this permutation LG, I write it by sigma, then apply sigma on the second row. So permute the rows by this permutation, then this is a permutation matrix. Permutation matrix. And so then you check that there is an injective group homomorphism from G into these permutation matrices. They have determinant plus minus 1 depending on the sign of sigma. So we have a injective homomorphism from G into GM, GLM, F. F is any field. Okay, because permutation matrices have entries are 0 and 1, they lie in every field. So therefore, every finite group is isomorphic to a subgroup of GL and F. This is called general linear group. The general linear group of invertible matrices, M by M invertible matrices with entries in a field. Okay. So study of finite groups can be reduced to studying subgroups of the group of square invertible matrices under multiplication. Are there any questions?
Yes, participants, anybody wants to ask question? If you have queries, then you can ask, please.
Yeah, you can write in chat box, or you can speak.
Or
So
you can.
the point I'm making is that the general linear group of invertible matrices of fixed size looks like a very concrete group. But you see, by this argument, every finite group is a subgroup of the group of matrices over any field you like. Yeah, we are identifying elements of G with permutations which are induced by left multiplication, and then these permutations are identified with permutation matrices. So pick a permutation and permute the row vectors of this identity matrix. Then I get a permutation matrix, and this gives a injective group homomorphism from this finite group into group of invertible matrices of size M by M, where M is the order of the group. So therefore, study of subgroups of the group of invertible matrices acquires importance. Yeah. So this is the largest group under multiplication that we are going to consider, and it has some very important subgroups. So we will be looking at 4 different types. There are many different kinds of subgroups of general linear group of matrices, invertible matrices, but we will focus on these 4 types of groups. So first is the orthogonal group. Orthogonal group of n by n orthogonal matrices. Okay, so what is an orthogonal matrix? So orthogonal n by n matrix. A, you have come across this while studying the spectral theorem for symmetric matrices, that if you have a real symmetric matrix, then it has a basis of eigenvectors, and the eigenvectors form a orthonormal basis. So the matrix which has the column vectors as eigenvectors of the symmetric matrix is an example of orthogonal matrix, and we can define it by saying that A times A transpose equal to A transpose times A equal to identity, and A has real entries. Real entries. Okay. Now this condition, A times A transpose equal to A transpose A equal to identity. If you just look at the matrix multiplication, then this condition really says that the column vectors or row vectors, okay, form an orthonormal basis. Of Rn. So orthonormal basis is just like usual basis, but in an orthonormal basis, the vectors have unit length and they are mutually perpendicular. Yeah. Okay. So now if you look at the definition of orthogonal matrix, if A and B, so first let us make a set ON. ON will be the set of all orthogonal matrices. Now, orthogonal matrices by definition, A transpose identity, so they are invertible matrices, and I'm looking at the entries in the real field. So invertible n by n matrices, which are orthogonal, look at this set and notice that if I take two orthogonal matrices and I multiply them, then they satisfy the same condition. This is equal to AB, B transpose, A transpose, but BB transpose is identity and A transpose is identity, so this is identity. Okay, and A transpose by definition of orthogonal matrix, A transpose is the inverse of A, and therefore, if I take A inverse transpose times A inverse, that is also identity. Okay, so therefore ON is a group, it's a subgroup of GLNR. Yeah. So this is the first result. You should remember that orthogonal n by n matrices, they constitute a group under multiplication, and it is a subgroup. Okay, it is a subgroup. Now inside ON, we will also study a subgroup called SON. So SON consists of matrices in ON whose determinant is 1. And this is, if I multiply two matrices of determinant 1, the product also has determinant 1, because determinant of product is product of determinants. And orthogonal matrix, just look at the definition, A transpose is identity. So if I take the determinant, it says that determinant of A and determinant of A transpose is same as determinant of A. So determinant of A square is equal to 1. But A has real entries, and therefore the square of the determinant is 1, means determinant is root of x square minus 1 equal to 0, but that has two roots, plus minus 1. So determinant of an orthogonal matrix is either 1 or plus minus or minus 1. Look at matrices which have determinant 1, orthogonal matrices which have determinant 1. So that is a subgroup. Okay, SON is a subgroup. Okay. Moreover, it is a normal subgroup. Note that SON is a normal subgroup. Can anybody tell me why it is normal?
Yes, participants. You have to say, yeah, Kavashkar is. Yes, Kavashkar.
Yeah. So Q1 to say 1 comma minus 1, we can do a map. So SLN goes to 1, the other values will go to -1. So maybe it will work out. So the kernel is exactly so.
Right.
Is it okay, sir?
Yeah, very good. So let me repeat what you said. So look at the determinant map from ON to plus minus 1. This is a group. This is a group under multiplication. It's a cyclic group of order 2. And determinant, by properties of determinant, this determinant is a group homomorphism. A mapping to determinant of A is a group homomorphism. And it is surjective. This is surjective because I can produce a matrix whose determinant is -1 and determinant of identity matrix is +1. Yeah. So this is a surjective map, and the kernel of this determinant map is set of all orthogonal matrices so that determinant of A is equal to 1. And the kernel is always a normal subgroup of any group homomorphism. Okay, so as kernel of a group homomorphism is a normal subgroup. Okay, SON is a normal subgroup of ON. Yeah. Okay, so already we have GLN. Okay, when we are considering groups over field of real numbers, we don't mention the field. So when I write GLN, it means it is invertible n by n matrices with entries in the real field. GLN contains ON as a subgroup, and ON contains as a normal subgroup SON. Okay, so I introduced these three groups to you. So these are over the field of real numbers. You can ask whether there are analogs over the field of complex numbers. So when it is field of complex numbers, we must mention. Okay, so that is GLNC, all invertible n by n matrices with entries in the field of complex numbers. That is a group, and the analog of ON is called UN. So UN is set of all matrices A, so that A star A equal to AA star equal to identity. Here, what is star? Star is conjugate transpose. So take conjugate of all entries of A and then take the transpose. Okay. So UN consists of all n by n matrices with complex entries, so that A star is the inverse of A. Okay. A star is the inverse of A. Computing inverse of these matrices is very easy. A star is the inverse of A. Okay. This is a group, just like I proved to you that ON is a group. Same argument proves that UN is a subgroup, and this is called the unitary group. Unitary group. And inside UN, I have the group of unitary matrices. Okay, group of unitary matrices whose determinant is 1. So A is in UN, so that determinant of A is 1. And by the same argument, this SUN is a normal subgroup of UN. Okay, so this is the special orthogonal group. SUN is the special unitary group. This is the special orthogonal group. ON is the orthogonal group, and UN is the unitary group. Yeah. So we are going to understand their geometry little bit. There is a lot of geometry in these groups. So these are called classical groups. So this is the terminology which was first coined by Hermann Weyl who had written a classic book on these groups. These groups are studied in many branches of mathematics, in topology, in number theory, in algebra, and they have beautiful properties. And I want to bring out just a few of these properties related to Euclidean geometry. Right? So any questions?
Yes, participants, you have any query, then you can ask. You just raise your hands if you have any query, then in that case, there is one option in reactions.
I think somebody wants to enter the class, Niza N.
Yeah. Abhinoy Paul.
It's okay, ma'am.
So you have query or you just?
It's okay. It's okay.
All right. Okay. So now let us begin with the small values of n. First of all, we are going to use in Rn. It is an n-dimensional real vector space. Okay, and we will often use the dot product of vectors. If u and v are vectors in Rn, we will think of them as column vectors. So as column vectors, these are n by 1 matrices. And the dot product of u and v, I will write this way. And as a matrix product, it is u transpose v. Yeah. So dot product can be written in terms of matrix product as u transpose v. And similarly, in the complex n-dimensional vector space, n-dimensional complex vector space, we have inner product, which is called the Hermitian inner product. Hermitian inner product. And it is defined in the same way. If I take two vectors, u and v, think of them as column vectors, then their inner product is defined as u star v. So u star is the conjugate transpose of the n by 1 column vector. So u is a column vector. When you take the conjugate transpose, it becomes a row vector. So take the conjugate of all the components of u and then convert this into a row vector. And this row vector times this column vector v, this matrix product is a complex number. And this is the inner product which we are going to use in n-dimensional complex vector space. And this will be called the Hermitian inner product. Yeah, I may just say inner product space, but most often the inner product that we use on Rn, real vector space, will be that of dot product of vectors. And in the complex n-dimensional vector space, it is the Hermitian inner product. Yeah. So let us understand some geometric properties of orthogonal matrices. Orthogonal matrices. So if I have an orthogonal matrix, if A is orthogonal matrix, then A transpose A is A transpose equal to identity. And this matrix A, it gives rise to a linear transformation. Yeah, it gives rise to a linear transformation LA from Rn to Rn, which takes a column vector u to A times u. Yeah, this LA is a linear transformation. Okay, what other properties this LA have? Can anybody tell me? Yeah, Sukanya Naik, you are asking U star V is mapped to R. No, U star V is a complex number. Yeah, U star V is a complex number. But if I take U star U, okay, if I take U, that is U star U, then this is a non-negative real number. And using this non-negative real number, we define norm of the vector U or length of the vector U, which is square root of U star U. Okay. So U star U is a real number, but U star V in general is a complex number. Okay, so my question is, if I take a orthogonal matrix, that is a matrix which satisfies this property, which is equivalent to saying that the column vectors of A or row vectors of A form a orthonormal basis of Rn. And now take linear transformation which is induced by A. Can you tell me some property of this? This LA is a linear transformation, but what else can you say about LA? What else can you say about LA? Is it 1-to-1, on-to, or what is it?
It depends, yes.
Pardon?
It depends on the matrix A.
I didn't get you.
Sorry, sir. It depends on matrix A. LA depends on, say, AU. Maybe the rank, maybe kernel depends on our A. LA depends on A, the matrix A.
Yeah, but I'm taking A to be orthogonal matrix.
Oh, okay, okay.
So if A is orthogonal matrix, then what is its inverse? Can anybody tell me?
Anybody more? What about the LA if A is orthogonal matrix?
Is this linear transformation invertible? Can anybody answer whether it is a invertible or what is its kernel?
Sukanya, are you saying something? Abhinoy, can you try?
I think it is invertible.
Yeah, what is the reason?
Kernel of this is singleton 0. So that's why this is 1-1.
Right.
And surjective also.
Yeah. So one-to-one linear transformation from a finite dimensional vector space to itself has to be surjective.
Surjective.
And that follows from what theorem? By rank nullity theorem.
Rank nullity, yes.
It is so LA is an invertible linear map because A is invertible. A inverse is A transpose. So if I compose LA with L A inverse, okay, it is equal to L A inverse, just from the definition. And this is the linear transformation induced by identity matrix, and that is the identity map. Okay, and similarly, LA inverse LA will also be equal to LI, which is identity map. So this is enough to see that it is an invertible linear map. But there is another important property of this linear transformation, which is induced by an orthogonal matrix. Okay, so suppose I start with two vectors and calculate their inner product, and now apply the linear transformation. The linear transformation will map U to AU and V to AV, and then take again the inner product. Okay, so we are taking the standard inner product, which is dot product. So this is equal to AU transpose times AV, and this is equal to U transpose A times V, but A transpose A is identity. So this is U transpose V, but U transpose V is the dot product of UV. So this says that LA preserves dot product of vectors. Yeah, is this clear to everybody?
Yes, sir. Yes.
Yeah. Now, once dot product is preserved, a lot of things are preserved. So if I start with two vectors, U and V, they have some angle between them. How do we find angle? Well, the dot product of U and V is equal to length of U times length of V times cosine of angle between them. Yeah. So the inner product, the dot product is preserved, and therefore dot product of U with U is same as dot product of AU with AU. But this is equal to length of AU square, and this is equal to length of U square, and therefore the map LA preserves length of vectors also. So I start with two vectors U and V. They have some angle between them, they have some length, but now I transform them by using this linear transformation by orthogonal matrix. Then these vectors are mapped to LAU and LAV. Okay, LAV. So, but their dot product is preserved. What I just proved is that this is same as this. Okay. So, and the length is also preserved. So this means that the angle is preserved. Angle between U and V is same as angle between LAU and LAV. So length of vectors are preserved, the angles are preserved. So if I take a rectangle and map that under this linear transformation induced by an orthogonal matrix, it will be mapped to a rectangle. A triangle will be mapped to a triangle which will be congruent to the original triangle. So the linear transformation which is induced by an orthogonal matrix preserves the entire geometry. Yeah, if you take a sphere, it will be mapped to a sphere in Rn. Yeah, inside R2, if I take a circle of radius 1 and apply the linear transformation by an orthogonal matrix, then if I take this vector, this has length 1 and angle, say theta from x-axis, the x-axis is mapped to x-axis. Yeah. So this E1 will be mapped to AE1. AE1 is the first column vector. It is the first column vector. Okay. And column vectors of a orthogonal matrix form a orthonormal basis. Yeah. So there will be AE1 will be some vector, but it will have unit length. AE2, if I take E2 here, the second basis vector, angle between E1 and E2 is 90 degrees, and that 90-degree angle will be preserved. Yeah. So AE2 will be still perpendicular to AE1, but vectors, there are two vectors which are perpendicular to AE1, either this vector or this vector. There are two possibilities here. Okay. So, but the angle, so their orientation may be reversed, but the angle will remain the same. The length of the vectors will be same when I apply this linear transformation. Yeah, so orientation may be reversed, but the length and angle will be preserved under the linear transformation, which is induced by an orthogonal matrix. So, and the same things will apply to unitary matrices. I'll come back to those. Yeah. So first, let us let us understand what can matrices in O2 do. So start with the very simple situation of the plane. So O2 is set of all 2 by 2 matrices which are orthogonal. So if I take a 2 by 2 matrix which is orthogonal, then the column vectors are unit vectors and they are mutually perpendicular. So first column vector, suppose first column vector is AB, then I know that A square plus B square should be 1. Yeah, because it's a unit vector. So when A square plus B square is 1 and A and B are some real numbers, then I can find an angle so that A is cos theta and B is sine theta. Okay. Now you take the second vector, column vector CD, then this column vector, call this as V and this as U, then V is perpendicular to U. Yeah, V is perpendicular to U and V is also a unit vector. Okay, so if this is cos theta, sine theta, and I want this vector to be perpendicular to this, then what are the possibilities? Just imagine geometrically. Okay, this vector has coordinates cos theta, sine theta, and therefore you draw a unit circle and suppose this angle is theta, then this is my vector U, whose coordinates are cos theta, sine theta. And the second column vector of this orthogonal matrix is going to be a unit vector which is perpendicular to U. Okay, a vector which is perpendicular to U. So there are two possibilities, either this or this. Yeah. So what are the coordinates of this vector? Can anybody tell me?
Yes, participants. Ishrat, can you try?
It's perpendicular to U and it's a unit vector.
Minus sine theta cos theta.
Yeah, but you see, the x
Minus
coordinate
cos
of this point is positive, you see.
Yes, sir.
So then, and y coordinate is negative, and their dot product should be zero, right? So what is the x coordinate?
Sine theta minus cos theta.
Minus cos theta. Yeah. And what about this? This is also perpendicular to you, this vector. What are its coordinates? See, this is 90 degrees.
It is minus sine theta cos minus sine theta cos theta.
Right, minus sine theta cos theta. Okay, so therefore, a 2 by 2 orthogonal matrix, I can write in this way: cos theta, sine theta, or one possibility is minus sine theta cos theta. Either this matrix, let us call this by r theta, and another matrix. There are two possibilities. Once I fix the first column vector as this unit vector whose coordinates are cos theta, sine theta, here it will be sine theta minus cos theta. Okay. Yeah. So this vector u, if I map it to this vector, what kind of geometrical transformation is happening?
Reflexive.
Sir, reflection.
Reflection, yeah. And if I map this vector u to this vector, then
This is also reflexive.
yeah, one of these. So just look at what is the determinant of r theta.
One, sir.
1. And determinant of S theta,
Also 1.
careful. What is the determinant of S theta?
-1.
Minus.
-1.
-1.
Yeah. So orthogonal matrices, A transpose identity means square of the determinant of A is 1. So determinant is either 1 or plus or minus 1.
-1.
So R theta has determinant 1 and S theta has determinant -1. Okay. Now this matrix R theta, okay, so we want to understand what is this linear transformation doing. Okay. In this case, I introduce a linear transformation. As we saw, every orthogonal matrix gives rise to an invertible linear transformation, and that invertible linear transformation is going to preserve length of vectors, inner product of vectors, angle between vectors. Yeah. So, but let us understand what is R theta actually doing. Okay, if I take a vector u, say let us take a vector e1, then e1 is mapped to R theta e1. R theta e1 is the first column vector of R theta, which is cos theta sin theta. Okay, so e1 is mapped to this vector, and e2 is mapped to R theta e2, and that is the second column vector. It is minus sin theta cos theta. And once I know action of a linear transformation on basis, I know the whole linear transformation. E1, E2 is a basis of R2. And so any vector is a unique linear combination of basis vectors. And therefore, if I operate R theta on W, it's a linear transformation. So it is X times LR theta E1 plus Y times LR theta E2. So this is equal to X times cos theta sin theta plus Y times minus sin theta cos theta. And you can simplify this. This is X cos theta minus Y sin theta, X sin theta plus Y cos theta. So we have found the action of this linear transformation on an arbitrary vector. Yeah. So if I take an arbitrary vector whose coordinates are xy, it is mapped to this vector under the action of R theta. Okay. Now, good exercise for you. Check that if this is the angle theta, then this is this vector LR theta operating on xy. So this vector, general vector, is rotated by angle theta in anti-clockwise direction. Okay, so use just some little bit geometry to see that this vector has these coordinates. So LR theta is rotation by theta of R2, all vectors in R2 in anti-clockwise direction. Okay. Yeah. So rotations are represented by 2 by 2 orthogonal matrices of determinant 1. So I took a matrix of determinant 1, orthogonal matrix of determinant 1, and showed you that linear transformation which is induced by this orthogonal matrix on the plane, on vectors in the plane, is that of rotation. It's a rotation by angle theta in anti-clockwise direction. Converse is also true, so that you should try this as an exercise, that if A is an orthogonal matrix, 2 by 2 orthogonal matrix, and LA is rotation by theta in anti-clockwise direction, then determinant of A is 1. And A has that form, cos theta, sin theta, minus sin theta, cos theta. Okay. So matrices in the the matrices in the orthogonal group of size 2 are of two types, either determinant 1 or determinant minus 1. And we have understood that if the determinant is 1, they are nothing but formulas for rotation by angle theta in anti-clockwise direction. Okay, let us look at, so any questions?
Participants, if you have queries, then you can ask, please.
Now look at S theta. Okay, S theta at determinant minus 1. Its column vectors were cos theta, sin theta, then sin theta, minus cos theta. So it is natural to ask what exactly this map doing. What is this map doing? What is the geometric characterization? What is the geometric meaning? Of LS theta? Yeah, this is different because the determinant of the matrix S theta is minus 1. It's going to have a different action. Okay. Yeah. So let us look at some special case to understand what it is doing. Right. So suppose I look at a linear transformation which fixes E1. E1 is mapped to E1, but E2 is mapped to minus E2. This is my linear transformation. Okay, let's call this T as this linear transformation from R2 to R2. To describe any linear transformation from R2 to R2, it is enough to say where the basis vectors are going. So I have given you the action on the basis vectors. If I take an arbitrary vector, it is equal to xe1 plus ye2, and that is equal to xe1 minus ye2. Yeah. So if I take a arbitrary vector xy with coordinates xy, it is mapped to x comma minus y. X coordinate remains the same, y coordinate becomes negative. Okay, so this T, therefore, this T is a reflection. It is a reflection with respect to x-axis. Is that clear? What is the matrix? Yeah, what is the matrix of T? Every linear transformation has a matrix. What is the matrix of T? Can anybody answer what is the first column vector of the matrix of T?
1, 0.
Yeah, second
1,
one.
0, 0 minus
minus
1.
0 minus 1. And what is the determinant?
Minus 1.
Minus 1. And it is an orthogonal matrix, right? The column vectors are unit vectors and they are perpendicular. Their dot product is 0. So this is in O2, but it is not in SO2. Yeah. And it is not giving a rotation, right? When you the matrix, when the matrix had determinant 1, it was inducing a rotation of the plane. Under rotation of plane, which vectors are fixed? Which vectors are mapped to themselves under rotation? Can anybody answer? If I have rotation as a linear transformation from R2 to R2, which vector is mapped to itself?
Those vectors whose are on x-axis. Zero vectors.
Zero vector only. It's if it is a non-trivial rotation, that is
Yeah.
some positive angle. It's a rotation with some positive angle. Then only the origin is fixed. Every
Yeah.
other vector will be displaced by angle theta. But this reflection, can you tell me what are the vectors which are fixed under reflection? Which vectors are fixed under reflection?
Sir, identity vector.
Yeah. All vectors on the x-axis,
Comma zero.
what happens to them?
They are fixed.
Yeah, they are fixed. Yeah, so rotation fixes only the origin. So if you take the rotation, the linear transformation which is induced by rotation, does it have any eigenvectors? The rotation is a linear transformation induced by orthogonal matrix of determinant 1. Okay. Does it have any eigenvector? Eigenvector of a rotation is a vector u which is mapped to itself, but it's a non-zero vector. But there is none.
So there is no eigenvector.
There is no eigenvector. There are no real eigenvalues, right?
Yes.
But if you take reflection,
Yes, we have.
there are
All
lots of
the-
eigenvectors,
On
right?
x-axis, large on x-axis.
Yeah, all vectors, non-zero vectors on the x-axis are eigenvectors. Whose eigenvalue is 1.
Yes.
And then the vector E2 is mapped to minus E2.
Yes.
So that's an eigenvector with eigenvalue minus 1.
Minus one.
Determinant is product of eigenvalues. Eigenvalues are 1 and minus 1, so it is minus 1.
Mhm.
So reflection is a very different linear transformation from that of a rotation. Yeah, but this is reflection with respect to x-axis. We can reflect with respect to any line. No, you take any line passing through origin. Take any line passing through the origin. Yeah. Maybe. Yeah. Take any line which is passing through origin. And suppose that the angle it has is theta. Yeah. This is the angle theta. And I want to reflect. I want to consider reflection with respect to this line. Consider reflection with respect to L. Okay. Now, can you give me a unit vector which is along the line L?
Yes, participants.
Yeah, take this
Cos-
vector.
cos- Yeah, cos theta.
Yeah.
Cos theta, sin theta.
Yeah. So call this as U. So U equal to cos theta
Mhm.
sin theta.
Mm.
Right. Now take a vector which is perpendicular to U. So this angle is 90 degrees. Okay. Under reflection with respect to L, if the mirror is along this line L, which has angle theta from x-axis, what is the action of this linear transformation? Okay. Let me call this linear transformation by T. Okay. and let us call this vector as V. So what is V? What are the coordinates of V? Yeah, X coordinate is negative and Y coordinate is positive.
Cos theta.
This is my V. Now under reflection, what is the image of V?
Minus V.
Minus V. And image of U?
U.
U. So is the linear transformation determined? U and V
Yes,
are perpendicular, right?
They are basis.
Yeah, so they form a basis. U and V, because they are perpendicular, this is an orthonormal basis.
Basis.
And therefore, if I want to specify a linear transformation, I have to say where the vectors U and V are mapping to. And I have given you the values of U and V under the action of T. So T is determined. Yeah.
Yeah.
So T is determined. And therefore, we can find the matrix of T. Matrix of T can be found. Exercise. How to find matrix of a linear transformation under standard basis? You have to take action of the matrix of the linear transformation on E1 and on E2. But you see, E1 will be a linear combination of U and V. E2 will also be a linear combination of U and V. So from the geometry of the situation, you have to express E1 as a linear combination of U and V. Yeah. So E1 is equal to say XU plus YV. How will you find X and Y? What is X? And what is Y? Yeah, but how to find them? See, U and V is a orthonormal basis. So every vector in R2 is a unique linear combination of U and V.
Yes.
So E1 is equal to XU plus YV. How to find X and Y? Yeah, anybody?
Anybody more?
You are asking us to find out what is X
X
and Y,
cos
right?
theta.
Pardon?
Is X cos theta, sir?
I'm not able to understand what you're saying.
X equal to cos theta.
You know, so if I am given this equation, I want to find X and Y. What will you, what?
We
You
will
know
get two
properties of-
equations, no?
Pardon?
E1 is 1, 0, so we will get two equations. 1 is equal to something and 0 is equal to something,
Yeah,
and then solve them.
yeah. But you see, you have access to dot product here.
So take the product of U or V.
Yeah, so
On both
take dot
sides.
product of U with E1, and that will be X, right?
Yes.
Isn't that better?
It is better, yeah, of course.
Yeah.
Yes.
And what is Y?
E1 dot V.
E1 dot V.
Yes.
So E1 is 1, 0. And what is U? Cos theta, sin theta. So that is cos theta, right? And what is Y?
Sin
Y.
theta.
Y is equal to 0, 1. I mean E1, sorry. Y equal to E1 dot V. So 1, 0. And V is equal to minus sin theta, cos theta. And that is equal to minus sin theta. And therefore, I have found formula for E1. E1 is equal to cos theta, okay, times U plus y equal to minus sine theta v. But I know u and v, you see, u equal to cos theta sine theta, and v equal to minus sine theta, minus sine theta cos theta, and this is equal to cos square theta minus sine square theta cos theta sine theta 2. So what is it?
Cos 2 theta sin 2 theta.
First one is
No.
1, right? The first one
Cos
is
2
1
theta,
square
sin
plus
2
sine
theta.
square.
Cos,
Sir, maybe minus inside plus, so cos square plus sine square, right?
The cos 2 theta, sin 2 theta.
The first,
are you sure?
Yes, sir.
Sine 2 theta and cos 2 theta. So you see, did I find now I have expressed E1, right? E1,
sir, this is the first one, sine square plus cos square, right? Because minus, it will become plus, right? And second one is 0, right? Maybe I may be wrong.
no, 2 cos theta sine theta.
Sorry, E1 equals to
Equal-
cos theta u minus sin theta v. And in place of you have put in cos theta sin theta. In place of v, you have written minus sin theta cos theta. Then minus sin theta that will be plus sin square theta.
Yeah,
Cos square theta plus sin square theta.
That
And
is
that
0.
one is-
that is
that
the,
is zero.
Second one
Yeah.
is 0.
yeah.
Yeah.
So you see, it is just a verification that what our vector is. I just showed this is equal to 1, 0.
Yes.
Sorry about that. This is just 1, 0. So I expressed E1, right? So what is TE1? TE1 is XTU plus YTV, right? Okay. And I know what is X. X is equal to cos theta. So cos theta times TU, but TU is equal to U. It is a reflection along the line L. So this TU is equal to U. And Y, I found Y as minus sine theta. So substitute minus sine theta. And TV was minus V, right? Because this vector V is mapped to minus V under reflection with respect to this line. So therefore, this is equal to cos theta. U was cos theta sine theta. Now it is fine. Minus sine theta and V. So this is plus, and V is equal to minus sine theta cos theta. Now it is fine. So this is equal to cos square theta minus sine square theta and 2 cos theta sine theta. So what is it?
theta sin theta. Cos 2 theta sin 2 theta.
Yeah. So the matrix of
Sin-
T, yeah,
Sin 2 theta, sir.
sine 2 theta.
2 theta.
So the matrix of this reflection, right? So this is my reflection along this. If this is theta, and then I'm taking reflection as a linear transformation of the whole plane, where this vector is mapped to itself and its perpendicular vector is mapped to its negative. Okay. then I have found the first column vector of matrix of T, which is cos 2 theta and sine 2 theta. A similar calculation, okay, similar calculation will be done for TE2. Instead of TE1, I will calculate TE2 by same method, and you will see that it will be equal to sine theta 2 theta minus cos 2 theta. So you see, determinant of T is -1. So this is an orthogonal matrix. Column vectors are unit vectors. They are perpendicular. And this is the matrix of this reflection. And the line is inclined at an angle theta. This line is inclined at angle theta. Now you see, this is 2 theta. Everywhere it is 2 theta. So we can write the matrix of reflection and matrix of rotation. And these are the two kinds of matrices in O2. O2 has two kinds of matrices. A, whose determinant of A is 1, and a matrix where determinant of A is -1. And this will give rise to reflection, and this will give rise to rotation. Yeah. So in general, what can we say about matrices in O2 and SO2? So, and we can ask the same question for O3 and O4, etc., etc. So what are geometric interpretation of matrices in, say, ON and SON? Let me show that any matrix in O2 is a product of at most 2 reflections. See, I gave you the matrix of reflection, right? If I want to reflect with respect to a line passing through the origin, I look at the angle between x-axis and that line, and then I can write the matrix of that linear transformation, which is reflection with respect to that line. So every reflection is given by a matrix, orthogonal matrix of determinant -1. Okay, but some matrices in O2 which have determinant 1, they give rise to rotation. What this theorem is saying, that even a rotation is a product of 2 reflections. We can compose 2 reflections and get a rotation. This is what this theorem is saying. So it is a special case of a more general theorem that matrices of reflections generate all orthogonal matrices. So this O2 is a group, and this theorem is saying that it is generated by reflections. And to understand a 2x2 orthogonal matrix, I will need at most 2 reflections. It's a product of at most 2 reflections. Okay, we will prove a more general theorem later, but let us prove this anyway. Yeah. So if it is, so we have seen that either any matrix A, if A belongs to
Yeah,
O2,
sir. Excuse me.
Yeah.
The similar result too in S3, sorry, O3 and O4 or something. The similar
Yes.
result.
Yeah, we will prove that.
Okay.
But I'm just looking at O2, which is a much simpler case.
Okay.
So if I take A in O2, SO2, then LA is a rotation. the linear transformation which is induced. This we have proved. If the determinant of A is 1, then it gives rise to rotation. And if A is in O2 and not in SO2, that means determinant of A is -1, then LA is a reflection. Yeah. So the theorem is true for such matrices because it's a reflection. If A is in O2, which is not in S2, it is a reflection. Therefore, it is a composition of at most 2 reflections. So we need to prove the theorem only for matrices which are in SO2. So we just need to show that any matrix of a rotation is a product of 2 reflections. It's a composition. You reflect 2 times, I will produce any rotation. This is what it is saying. Okay. So let us take such a matrix of a rotation. Yeah. If I take such a matrix, okay, if I take such a matrix, I want to prove that it is a product of 2 reflections. So any rotation matrix, we have seen the structure. The column vectors are unit vectors. They are mutually perpendicular. Determinant is 1. So any matrix of rotation looks like cos theta, sin theta, minus sin theta, cos theta. So any such matrix which is in SO2 looks like this. But if I multiply this matrix by matrix of reflection with respect to x-axis, matrix of reflection with respect to x-axis maps E1 to E1, but it maps E2 to minus E2. So first reflect with respect to x-axis and then rotate by angle theta in anti-clockwise direction. So A times, call this matrix as R. So A times R is this matrix, but what is it? This is equal to minus sin theta. Okay, and yeah, just a minute. Yeah, what is the product? Is minus sin theta, and this is sin theta, cos theta.
What is R, sir, here? What is R?
No, so I think my R is wrong.
Oh, yeah,
R,
I think so.
Yeah. So
Yes,
R
yes.
maps E1 to E1 and E2 to minus E2. This is my R. That's why I was getting confused what is going on. Yeah, so this is fine. Okay. Now what is this product? This is cos theta. Okay. And this is sin theta. Then sin theta minus cos theta. And do you recognize this matrix? What this matrix is going to do? What geometric transformation this product matrix represents?
Reflection.
And what is the inclination of that line with respect to x-axis? So
Along x-axis.
LB is reflection with respect to
X-axis.
no. It is reflection with respect to line which is at an angle theta over 2.
Theta by 2. Yeah.
Yes.
Yes, because the 2 times theta, right?
Right.
Yeah,
So
yeah.
A times R, the linear transformation which is induced by A times R, you know it is linear transformation induced by B, which is a reflection. This is a reflection. But LAR is same as LA composed with LR. And this is LB. But these are the invertible linear transformation, right? We saw that these are all invertible matrices. The linear transformation are invertible. And therefore, LA is equal to LB composed with LR inverse. What is R inverse? R is reflection, you see.
So R inverse of reflection is again a reflection.
Exactly. R square is identity. If you reflect 2 times, it becomes identity. So it is LR.
Yeah.
So what I have done, so this says that this matrix A, orthogonal matrix A, which represented rotation, is a product of 2 reflections. You see, this is a reflection and this is a reflection. Both are reflections. So I have proved that any rotation is a composition of 2 reflections. Yeah. Any reflection is anyway product of at most 2 reflections. So this proves this theorem that any matrix in O2 is a product of at most 2 reflections. And this is a special case of a beautiful theorem due to Cartan, Elie Cartan. And it was later generalized by Dieudonné. It says that any orthogonal matrix n by n is a product of at most n reflections. So you might wonder, what is the meaning of reflection? This n by n matrix. So an n by n matrix, when do we say an n by n matrix gives rise to a reflection? So I want to introduce reflection in Rn. So you have understood reflection in R2. You want a linear transformation which is a reflection, then it is going to be reflection with respect to a line which has inclination theta with respect to x-axis. And we worked out the matrix of this linear transformation, which is reflection. And the matrix of this linear transformation was cos 2 theta, yeah, sine 2 theta, sine 2 theta minus cos 2 theta. That was the matrix of reflection. Now, if suppose I'm given, I want to understand what is reflection in 3-dimensional space. Okay, 3-dimensional space. Let us say reflection with respect to the xy plane. Reflection with respect to xy plane. So where is this vector mapping to?
xy minus z.
Xy minus z. Yeah. So what is the matrix of this reflection? Matrix of T. E1. E1 is mapped to E1, right? And E2 is mapped to E2. E3 is mapped to this. That is the matrix of this reflection. So we fixed a plane, which is XY plane, and wrote its matrix. But I can take an inclined plane, right? A plane which is passing through the origin. So take a plane in 3-dimensional space. Plane in 3-dimensional space. And we want to understand what is the meaning of reflection with respect to this plane. Then vectors which are perpendicular to this plane should be mapped to what?
Yeah.
If u is perpendicular to this plane,
Minus u.
minus u. And vectors inside the plane?
To the same. To
Same.
themselves.
Right, right. So we are looking for a linear transformation from Rn to Rn, which will map u to minus u, and it will map TV to V for all V in this plane. And this vector u is perpendicular to this plane. Okay. Yeah. So you play around with this in R2, and this is an exercise for the tutorial. You should think about this, how to write a formula. Yeah, you can even play in R2 and R3, and you can write a formula for this linear transformation. But yeah, so that's an exercise for you to come up with a formula using geometry. Okay, but let us look at this matrix identity minus 2u transpose. Suppose I take a unit vector and look at a plane which is perpendicular to this unit vector. This is my unit vector, and take this plane which is perpendicular to u. Now this u is a column vector, u transpose is a row vector. So this is an n by n matrix. What is the rank of UU transpose?
N.
UU transpose. What is the rank?
Anybody more? Yeah.
So 1.
Very good. This is a rank 1 matrix. Yeah. So another exercise, any rank 1 matrix, n by n, is of this form for some vector. Yeah. So I'm looking at this matrix I minus 2UU transpose. This is my matrix. Let us see its action on U. This is equal to U minus 2UU transpose U. What is it?
Minus
What is U transpose U? U transpose U?
So 1.
Yeah, that is the square of the length of U. The length of U is 1. So therefore, what is a U?
Minus u.
Minus U. Isn't that what we wanted? We were looking for a matrix of reflection with respect to the plane which is perpendicular to U. So U must be mapped to U, and this matrix maps U to minus U. But now let us take a vector which is perpendicular to U and see what A does to this. So this is equal to V minus 2UU transpose V. And what is this?
Zero.
0, because U transpose V is 0. It is near perpendicular. So this is equal to V.
Yes.
So you see, that is the matrix. This is the matrix which does the wonder. So this is called the householder matrix. Householder matrix. Okay, this householder matrix HU is I minus 2UU transpose, and length of U is 1. And the linear transformation which is induced by this householder matrix is reflection with respect to the plane which is perpendicular to you. Yeah. So our time is finished. and I will continue next time.
Why the name came householder, sir? I just want.
Householder is the mathematician who constructed this matrix first in numerical analysis. In numerical linear algebra, this matrix is used very often. It is a principal tool to do eigenvalue computations. It's a very important matrix. But this is the matrix of reflection in n-dimensional space with respect to a plane which is perpendicular to this unit vector. So you see, we derived a formula for reflection with respect to a line in the plane, right? You go back and solve this exercise that I can write the formula for reflection with respect to a line in the plane by using the householder matrix. So if I am giving a line in the plane passing through the origin, I have to just find a unit vector perpendicular to that line. And then this HU gives the formula for the linear transformation, and it will be exactly the formula that I derived. Okay, so it's a wonderful matrix. It gives you at once the formula for reflection. And we will prove next time that any orthogonal n by n matrix is a product of householder matrices. So householder matrices are the building blocks of all orthogonal matrices. So the orthogonal group is generated by householder matrices.
Oh, okay. Wonderful.
That's what we will prove next time.
Okay,
I
sir.
proved this already for O2, right? In O2, I proved that any rotation
Yeah, yeah.
matrix is a product of at most two reflecting
most.
matrices. Yeah.
Okay, sir. Thank you.
I will generalize this next time to n by n orthogonal matrices. So I will stop here.
Yes, sir, sure.
Thank you.
Thank you so much, sir, for your wonderful lecture.
All right. I have to conduct another online course, so I will take your leave. Yeah.
Yes, sir. Okay, sir.
Okay.
Sure, sir. We
Okay.
can. Thank
See you
you, sir.
tomorrow.